So let's start by going over the examples that were on the board in class. So number one, you should have injective, which is one-to-one, but not surjective. And in order to describe why not, you would say something here like C has no preimage, or why it is not onto. We do have a bijection in number two. Number two is the only function that is invertible, and so that's something that you should write down in your notes, that only a bijection is invertible. All right, invertible just means we can find the inverse. All right, so a function must be both one-to-one and onto to be invertible. Over here, the function's not one-to-one. To justify that, using the definition that we were given, we would say something like f of 1 equals f of 2, but 1, oh, I don't have a symbol on my keyboard for does not equal, so let me grab this, but 1 does not equal 2. All right, that's making use of the definition of one-to-one. And then over here, we are one-to-one because every input has a, actually, oh, I'm sorry, we're neither here, are we? Not one-to-one. Because two different values both map to D. Okay, so same reason over here. I would say f of 3 equals f of 4, but 3 does not equal 4. Or I could say something like D has more than one preimage. Okay, so one-to-one means everything must have a unique preimage. So let's take a look at this with some functions. All right, so a function mapping from Z to Z. Remember, Z are the set of integers. And if I were to graph this, first of all, I'm going to make a little table of values with some integers here. If I were to graph this, you would probably say, oh, wait, that's just a straight line. But since we're only considering integers, when we graph it, we don't connect the points. We would just plot some points here, and then we'd have this, -2, 1, and we would just plot points, and it would look like this. Okay, I would not connect them. So clearly it's one-to-one. If I plot this, it would pass the horizontal line test, right, for one-to-one. And then is this onto? So to figure that out, you'd have to ask yourself, for every element in the codomain, right? Do I find an element from the domain that maps to it? Okay, so if we were in class, I'd say, give me any integer, right? And somebody would give me something like 100, okay? And I could find an element in the domain, which would be 97, that would map to that. And that is true for every possible element in the codomain. Therefore, the codomain does equal the range, and therefore this is both one-to-one and onto. I'm going to use these official words also, so we get practice with these. That means it's injective and surjective. Which makes it a bijection, which makes it invertible, right? And clearly the inverse function would just be x minus 3, right? That's how we would find the inverse function. All right, so since it's a bijection, it's invertible. Okay, because if I wanted to take the 100 and get back to the 97, I would just subtract 3. Now this next function, I am going to map from R to R. So from the set of reals, all reals to the set of reals. And we should recognize that as our standard parabola. And if I do this, right, draw the graph, clearly I can see it's not one-to-one. It would fail the horizontal line test. And then is it onto the set of all reals? So it's not one-to-one. And the problem with the onto part, as I'm going to say not onto, because all of these values down here, all of these negative values do not have a pre-image. And so then you might wonder, well, wait a minute, how is it possible then that, we talk about the inverse of f of x equals x squared. The inverse of squaring is square root, right? So we do know, okay, we do talk about an inverse function for this. But what we would do in that case is we would have to restrict the domain and the range both to a place where the function would be an onto and one-to-one function. Okay, and if I restrict the domain, and by restricting the domain, that thereby restricts the range also. If I restrict, so I would actually, and I can include 0. So the way that I want to say all reals greater than or equal to 0 is like this. That's one way I can write that. Okay, and then if I restrict the domain, that leads to a restriction in the range as well. And from mapping from this set to this set, I do have a function that is both one-to-one and onto. I get a bijection. Okay, so this function is defined only when inputs are greater than or equal to 0, and then outputs, therefore, will also be greater than or equal to 0. So let's look at how our range and codomain really affect whether we are one-to-one or onto. So let's take a look at this function, and I'm mapping from z to z. And if I graph it, I do get a linear function. I hope all of you can recognize that it would be a straight line. Linear functions are always going to be onto, of course. And finding a table of values, what I should notice, though, is if I wanted to get an output of, say, 1, right? So is this function onto the integers? And if I looked at this and said, okay, well, how could I get a 1 out, right? What about a 1? What would map to a 1? And the problem is that the value that would map to a 1 would not be an integer. So if I'm only inputting integers, so notice if I solve for x, I'm going to get -1/3. That's not an integer. All right, so therefore, from the set of integers to the set of integers, I am not onto. Okay, so this would be one-to-one, but not onto. Okay, so it's injective, but not surjective. All right, from z to z. Now, if I took this function and changed the inputs and outputs to all real numbers, if I'm allowed to input a value like 1/3, right, then I could get out all integers, right? If I were allowed to input all reals, I would be on to the integers. If I changed this, then, mapping from all reals to all reals, then it is both one-to-one and onto, because then if I graphed this, I would connect the points, and any value, right, my codomain would include all possible y values. No matter what I put in for y, I would find an x that maps to it, I'm sorry. So this would be the x that would map to whatever y value I was looking for. So it is onto. So drawing and representing the functions graphically is certainly a helpful way to do these. So over here, if I graph this, I hope we recognize the appearance of a cubic. And this would just take my standard cubic and it would move it over 2 units. So it would look like this. I would encourage you to graph this on a graphing calculator. Okay, but this would pass the horizontal line test. And any y that I found, no matter where I picked my y, right, I could find an x that maps to it. So every possible value in the codomain has a pre-image. So because we're mapping from R to R, this one would be both 1-to-1 and onto. So looking at the graphs can be very helpful. And again, we can see the changes from which sets we're mapping from and to. Okay, if I were doing this from Z to Z, it would still be 1-to-1, but I wouldn't be able to output every possible integer from this. And therefore, it would not be onto. So let's look at some other interesting functions down here. These are what are known as functions of 2 variables. I'm inputting an ordered pair. And therefore, I'm going to map from the set n cross n. So we talked about that in the note packet the other day. This n cross n is the set of all ordered pairs of natural numbers. Okay, so I might have 3, 3, 1, 2, I don't know, 5, 5, 11, right? Just any ordered pairs of natural numbers. And what this says is to input them, square each, and then that's your output. And so the output will be another natural number. So is this 1-to-1? So why don't you think about that for a minute? Like I'm going to input this, and I'm going to output 1 squared plus 2 squared, which is, that'll output a 5. Okay, this will output 9 plus 9 is 18. So would there be a different output that could also give me 5? And I hope it doesn't take you too long to realize that if I just went like this, then this would be a different set of ordered pairs, but I would get the same output. Okay, so it's not 1-to-1. And then is it onto? Could I, for every possible natural number, find the sum of perfect squares that adds to it? And that would not work. For example, I don't know how I'd get 3, right? I mean, if I square 1 and square 1, right, or square 1 with squaring 2, that's never going to get me 3. So this one would be neither 1-to-1 nor onto. Okay, so this one's similar. So plug in here, and but this time we've got z cross z, so that just means we're including negative numbers as possible values in our ordered pairs. So if we just try a few, you know, what would this be? And again, is it 1-to-1? Right? Could I just got -5. Is there another way that I could get -5? Okay, certainly if I plug in 0, 5. right? Then I'm also going to get -5. So obviously it's not on 2. And is it, I'm sorry, I just misspoke. Obviously it's not 1 to 1. Obviously it's not 1 to 1 because I just got -5 using 2 different inputs, all right? And there would be many more sets of ordered pairs that I could plug in that would give me -5 as an output. But when I look at my integers, is it possible to get any integer as output? If I listed all my integers, could I find something that would give me these as outputs? And the easiest thing that I could do for any integer is I could just go, I could just plug in 0 and then the opposite of that integer, right? And that would give me, if I wanted to say, what's going to give me an output of n, right? For any n as an output, right? So if I want to get an output of -4, then I could just plug in 0, 4, and that would give me an output of -4. So therefore, what that tells me is that this one is on 2, okay, but it's not 1, 2, 1, but it is on 2. All right, so let's stop here and take a break.